Alrighty, this is going to be kind of an analysis of how to do problem number 46. Now I wanted to do this in video lesson form because I could give you the key, but the key really wouldn't just give you justice to how I would solve this problem. Okay, now, first thing, you've got a cyclical process here. We go from point A to point B, from point B to point C, and then C back to A. So we've got constant pressure processes, constant volume processes, and then changes therein. Now, we're talking about the same old pressure-volume diagrams, so that means we've got pressure going up the vertical, volume going down the horizontal. So, pressure, volume. It does give you a little bit of information in here that we are going to use later, but for right now I'm just going to write it in here. Alright, it says that Vs equals 4 meters cubed, and PS equals 40 pascals. So all that's trying to do is give you a general scale for exactly how big this thing is. Pardon me. Now, that is not exactly important as of right now, but I will show you how that goes in here later. This is 40 pascals. This is from here 4.0 meters cubed. Okay, now the first and the biggest part of this is determining what's going on with the individual steps of this process. In other words, with the first law of thermodynamics, what is going on in situation A to B, what's going on from B to C, what's going on from C to A. Now, anytime you draw these, it is very important to make sure that you are drawing the arrows that depict direction onto the cycle, because that is going to change what's going on here. Right now, we draw up this chart the way that we've got it. A to B, and we've got Q, W, delta E internal. Q, W, delta E internal. Get a nice little chart here, and it's just asking you general trends. Is it going to be positive? Is it going to be negative? Is it going to be zero? So we've got A to B, B to C, C to A. Now the ones they already give you, we've got a plus here and a plus here. Plus and plus. Now I will tell you that the easiest one to solve for is going to be this guy right here. This column right here. The work is going to be the easiest to work with because that's the only one that we have a math equation that goes along with it. The amount of work done on one of these PV diagrams equals the integral from VF to VI P dV. Okay? So, basically, work is the area underneath this curve. But what we can do is we can just look at the general trends here and see if we can figure out if this is going to be a positive work, a negative work, or zero work. Alright, so let's look at situation from A to B to try to determine what this is first. So from A to B, that means we're going from some value for volume that is higher and cutting it back to some volume for work that, we're going from a lower volume to a higher volume. So that means that my initial volume is going to be smaller, my final volume is going to be bigger. Alright, so that means VF minus VI is going to be some positive value. Alright, because VF minus VI is going to be some larger number minus some smaller number, meaning that the work is in general going to be positive right there. Now let's look at the other situations here. From B to C. On B to C, notice that the volume stays exactly the same. So VF and VI are going to be the same value. So anytime you take any number and subtract it from itself, you're going to get the same exact thing out. So VF minus VI equals 0 in this case. Now also, you can look at this in another way to figure that out. This is a constant volume process, which is one of our special cases. In a constant volume process, the work done equals 0, and that also means that the change in internal energy is going to have to equal just my Q. Well, by knowing that, I can actually solve two things at the same time here. The constant volume process means that my work is 0. I have no area underneath a single straight line here, a vertical line. But my change in internal energy is going to equal my Q value. So, Q is positive. My change in internal energy then is going to have to be the same exact value. Alright? Now, let's look at the work going from C back down to A. Now my initial value for volume is going to be a high volume, and it's going to go down to a low volume. So when I go from final to initial, final minus initial, I'm going to have a lower number minus a higher number. So anytime you have a smaller number minus a bigger number, that means that you're going to, in the end, have negative work coming out here. Okay? Now, here's where the tricky part comes. Trying to figure out the Q's and the delta E internals. Now, I'm going to figure this one out first. My delta E internal is going to be equal to, well, notice what we've got here. We've got a full cycle or a cyclical process. Another one of our special cases was anytime that you have a cyclical process, change in internal energy is 0. Well, let's see what we got here. So I've got some positive value here. I've got some positive value here, which means that the only way that I can get the total internal energy, the total change in internal energy, to equal out to be 0 is to have a negative value right there. Alright, so good. We figured out this one. Now the hardest part, the Q values. Pardon me. Now this will be a little bit easier when we talk about next chapter. In the next chapter, we're going to go through the ideal gas laws. We're going to go through some of the other gas properties that are going to make this a little bit easier to identify. But in general, let's see what we can figure out through this. Now with these ones, I'm going to go back to a math equation. The change in internal energy equals Q minus W. Alright, so I've got 2 out of the 3, so I might be able to figure out what the third one is going to be based upon that. So if I've got some positive value over here and some positive value over here, because my delta E internal and my W are both positive, in order for this to come out to be a positive value, that means that my Q has to be a pretty big positive value, because I have to take a positive value minus a positive value and still get a positive value. So that means that my Q here has to be positive. It's the only way I can get it to work out. Right now, on the bottom one, it gets a little bit trickier here. My change in internal energy is negative, and my work is negative. Now here's where it could get really, really tricky, because literally, depending on the size of some of these numbers, it may or may not work out. Okay, so if I need a negative number over here, and I know I have a negative number right here, depending on the size of this Q, it could be either one. Right? But let's just say in general, well, minus a negative, think about this. If we take minus a negative, that's the same as saying that we have a positive value. So, because I have a small positive, that means in order for the change in energy internal to be negative, I need this to be at least a negative value. So, here is your chart. Positive, positive, positive across the top for A to B. Positive, 0 positive from B to C. Negative, negative, negative from C to A. Okay, now that is the first part of this problem. The second part, it asks you for the total work done in the entire situation. So, anytime that you're talking about a cyclical process, the area enclosed by the curve is going to make up the work done in that process. So in this area here, what I'm shading in blue, this is going to be my total work done. Okay, now The nice thing is, because this is a nice little geometrical shape, I don't have to sit there and try to figure out calculus-wise what this is going to be. I know that the area for a triangle equals 1/2 the base times the height. Through the scaling, I'm going to sneeze here in a second, and I apologize. I'm going to move. Sorry about that. So, right, as long as I can tell how big the base of this triangle is and how tall the height of this triangle is, I can figure out what the area of it will be. Now, I showed you in a previous video lesson that when you take the pressure, which is in pascals or newtons per meter squared, and you multiply it by volume, which is in meters cubed, you end up with Newton meters, which happens to also be joules, which will tell us how much work is being done. The base of this, if this scale is set to be 4 meters cubed across the bottom, it takes up half of that, so that is 2. This takes up half of the 40, which would be 20. 2 times 20 is 40. 1/2 of 40 is 20 joules of work. Okay? Now, if there are any problems, any questions, or anything else beyond this, please let me know. Email, whatever you got to do, and get the information to me. I will do my best to get the answers to you as quickly as possible. Now, please continue working on the study guides. And also, the one other thing I'm going to say, I did give you practice or typical questions that might be in the form of a multiple choice question. The next test will include 4 to 5 multiple choice questions, which are going to be relatively similar to what you have seen on that list. So, give that a try, see where you end up, and please ask me if you have any problems. Good luck, and we'll see where we end up.